Here is the challenge we will consider. We want to implement an exclusive OR gate, but we are given only NAND gates. How can we do this? Well, first let's remember the truth tables for these two gates. For our exclusive OR gate, we list all possible inputs, and by convention we write it in order in terms of binary 0, 1, 2 and 3. Our exclusive OR gate means that the output is a 1 only if exactly one of the inputs is a 1. So it looks like this. Our NAND gate is the opposite of an AND gate. An AND gate is a 1 only if the two inputs are a 1, and this gate's the opposite. So its truth table must look like this. While there might be simpler techniques for solving this particular problem, we are going to look at a general technique, and the starting point is to take our truth table and to write it in a canonical form called sum of products form. This will work for any truth table, not just a 2-input truth table, but even a 10-input truth table or a 100-input truth table, although of course you'd run out of time doing that by hand. The first trick is to realize that I can implement this exclusive OR gate if I can first of all create two other gates, and all I'm doing is identifying where the ones are at the output, and I pick the first one and I want to recreate it here, and I pick for my second gate over here, I want to implement the second one here, and if I OR these two together, so now I'm making up symbols here, of course these gates don't exist, but if for example this gate looked like a, what shape can I draw? Maybe this funny shape. And if this logic gate over here looked like this funny shape here, then I can create my exclusive OR gate by taking my first logic gate here, taking my second logic gate here, and ORing them together. And for the inputs, I need to connect the two inputs together like that for one input, and these don't connect here, these don't connect here, and these would be my inputs. So let's first make sure we understand this clearly. The claim is that the truth table for this blue diagram is the same as the truth table for my exclusive OR. So let's work out the truth table for this new circuit down here. So to work out the truth table for any logic circuit, I simply go through the inputs one at a time. I ask, if I put in 0, 0 into this circuit here, what do I get at the output? So let's do that. I put in 0, 0. This 0 flows through, so I have a 0 coming in here, and this 0 flows through, and I have another 0 coming in. According to the truth table for this logic gate, if I have got two zeros coming in, I have a 0 coming out. Similarly, for the logic gate at the bottom, I've got two zeros coming in. We can trace those paths through. If I've got two zeros coming in to this logic gate here, then I have a 0 coming out. So I have a 0 here. And now this last logic gate is my OR gate, and the output of an OR gate is a 1 only if both of its inputs are 1. In this case that's not true, so the output must be a 0, and I can write down 0 here. If we now speed it up and take some shortcuts, so I encourage you to go through this the slow way like I did for the remaining 3 possible inputs, but the faster way is to do it as follows, and you can do it this way with a bit of experience. Let's assume 0, 1 goes in. So if 0, 1 goes in, and I'm not writing it down because we can do this in our heads once we're used to it. So if 0, 1 goes in, then I can see that means I've got 0, 1 going into this gate, and I have 0, 1 going into this gate. If 0, 1 goes into this gate, then according to this, I have a 1 coming out. If a 1 comes out, then an OR gate, as soon as any of the inputs is a 1, we know the output is a 1. Therefore, I immediately know that in this case I have a 1 coming out. Now I move on. If I have a 0, 1, if I have a 1, 0, 1, 0 here comes in, so I have a 1, 0 here. This logic gate tells me that if 1, 0 comes in, I have a 1 coming out. So a 1 will come out, and anything ORed with a 1 will give me a 1. So again, I quickly know that this is a 1. And finally, to work out what happens if I've got 1, 1 going in, well, I've got 1, 1 into here, and according to this, I have a 0 coming out. And I have a 1, 1 going into here, and according to this, I have a 0 coming out. So 0 ORed with 0 gives me 0, and very quickly, I've worked out that that's a 0, and that proves our claim. We have shown that an exclusive OR logic gate with this particular truth table here has got exactly the same truth table as this circuit down here, because there is the truth table and it's identical. So we're halfway there. We're able to represent this truth table here as a bunch of funny things, but they're all ORed together. And in Boolean algebra, we often write an OR using the mathematical plus symbol. For those that are mathematicians, there's a reason for that, but we don't have to worry about it. So an OR is a plus. A plus is a sum. We sum things up, we add them up. And remember, I said at the start that we're going to write this truth table in a particular way as a sum of products. And here's our sum. We've got an OR gate here. We just have to write these guys here in terms of products or AND gates. And there's a special way we can do that as well. To summarize so far, given an arbitrary truth table, we look for when the output is a 1. Each time there's a 1, we're going to create, so to speak, a new logic gate, and that logic gate is going to have a truth table such that its output has only a single 1, and it's going to be in the right location. So here I've got 2 1s in the second spot and the third spot. So I need one logic gate that gives me a 1 in the second spot, and I need another logic gate that gives me a 1 in the third spot. And then we can see that to get the truth table that we want, all we need to do is take these intermediate truth tables and OR them together. And then the output is going to be exactly what we want. To elaborate, because we are going to send the same inputs to both of these gates, when we OR them together, then the output is going to be whatever the input is. Say the input is 0, 1. So I look at 0, 1 here, and I look at 0, 1 here, because the same input's going to go to both these gates. And the output's going to be the OR of them. So if 0, 1 comes in, the output's going to be 1 ORed with 0, which gives me a 1. And that's indeed what we have here. So very quickly, if 0, 0 goes in, the output's going to be 0 ORed with 0, which is 0. If 0, 1 comes in, the output's going to be 1 ORed with 0, which is 1. If 1, 0 comes in, the output's going to be 0 ORed with 1, which is 1. And if 1, 1 comes in, the output's going to be 0 ORed with 0, which is 0. And this agrees with using plus, because intuitively 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. Tangentially, you might worry about 1 plus 1. Well, the rules of Boolean algebra is that 1 plus 1 is equal to 1, because we define plus to be the or sign. And for mathematicians, you can actually show that that works. That actually gives you a sensible algebra to work with. Anyway, that situation does not happen here because remember, each of our devices is only going to output a single 1, and by design, different devices output a 1 in different locations. The next step is to write each of these gates using only AND gates. Now in general we can't do this, but because each of these has the very special property that there's only a single 1 at the output, it turns out that we can do it. Well, almost. I told a small lie. We have to also use NOT gates. And once we see this, this makes perfect sense. First, let us remember what the truth table is of an AND gate. If I have an AND gate, its truth table is going to be 0, 0, 0, 1. And notice that an AND gate has only a single 1 at the output. That there's only one time when the output is a 1. And that's true of this gate, and that's true of this gate. So we just somehow have to rearrange the rows of an AND gate, and we're done. Well, how can I rearrange the rows of an AND gate? Well, a moment's thought shows that I can do that by adding an inverter to one of both inputs. So let's have a look at what happens if I add an inverter to the first input of my AND gate here. So what is the truth table for this device? I have an inverter here and I have an AND gate here, and I want to know the truth table. So same as before, my truth table, I write it out like this. I first put in 0, 0. What happens? This 0 goes through and gives me a 1. This 0 goes through and it stays a 0. 1 and 0 is a 0. Okay, what if I have 0, 1 going in? Well, now I've got this 0 goes in and gives me a 1 here. This 1 goes in and gives me a 1 here. And 1 and 1 is a 1. And you can work out similarly that that's going to be 0 and that's going to be 0. And we see that indeed we have been able to rearrange the rows of the truth table for an AND gate to get another logic gate which has got a single 1 at the output. And a little bit of thought shows us why this is true. For the output to be a 1 here, this input has to be a 1 and this input has to be a 1. Whenever there is not an inverter, that means the corresponding input has to be a 1. And whenever there is an inverter, that means the corresponding input has to be a 0. So based on this idea, we can immediately write down a logic gate to implement this truth table here. How do we do it? Well, we simply look to see when the output is a 1. And we see that to have the output being a 1, we need the first input to be a 0 and the second input to be a 1. And that tells us that the first input has to be a 0, so I put it through an inverter to make it a 1 when it's a 0. And the second input has to be a 1, so I leave it there. And I put that through my AND gate, and Bob's your uncle, I get the correct truth table. For this one over here, the same logic tells me that to get my 1 at the output, the first input has to be a 1 and the second input has to be a 0. So the second input I put through an inverter. So that now at this point here, when the input is 1, 0, I have got 1, 1 at this point here. And that's the only time I will get a 1, 1 here. And when I connect it to an AND gate, that's the only time I'll get a 1 coming out, which means that this circuit here implements this truth table here. Finally, if we want a circuit diagram, I just have to connect the output of this one and the output of this one into an OR gate to get this guy here. So let me clear the bottom half of the screen and show you that. In fact, let's just do the whole thing in our heads from the start. So I want to write this logic gate in the sum of product form. So I look at the first row, there's a 0 at the output, so I do nothing. I look at the second row, there's a 1 at the output, so I need to do something. I need to write down a logic gate that will give me a 1 if and only if the input is 0, 1. And I know that an AND gate is going to give me an output of 1 if and only if both its inputs are 1. Now I want the second input to be a 1, so I leave it, but the first input I'm detecting when it's a 0, so I need to put that one through an inverter. So now this circuit here, the one in green, it's going to implement this logic gate over here. It's going to give me a 1 if and only if the input is 0, 1. Now I go down and look at the third row. It's also a 1, so I need to do something. I need to do the same kind of thing. I need to write down a logic gate that will output a 1 if and only if the input is 1, 0. And so I know I can do that using an AND gate, because the output of an AND gate is only going to be a 1 for a particular input and no other. I want the first input to be a 1, so I just leave it like that. The second input needs to be a 0 if the output's a 1, so therefore I put that through an inverter. And now I have a logic gate here that's implementing this truth table over here. It's going to be a 0 except when the input is 1, 0. Because if the input is a 1, 0, then 1 goes through here, 0 gets inverted to become a 1, and 1 is a 1. Finally, to get my exclusive OR gate, I just need to take these outputs and OR them together, because remember, I just have to OR these two separate gates together here. Of course, mine are bookkeeping, and I can cheat and do it two ways. If I call this input A and this input B, then I can just write AB, AB. And that's a cheating way of saying that they're wired up together. If you don't like that, then you're going to have a messier diagram where this is input A and this is input B. And so my AB goes through an inverter, and one that doesn't into an AND gate. Down here this goes through into an AND gate while this one gets inverted, and then these two go through to an OR gate. And here we have it. We have created, using only AND, OR and NOT gates, and OR and NOT gates, we have implemented, in this case, an exclusive OR, but this process will work with anything. So given any truth table, we can implement it using this sum of products method. ORs are sums and refers to this sum here, and AND gates are actually written as products. And that makes some sort of sense, because for the truth table for an AND gate, it's 0, 0, 0, 1, and 0 times 0 equals 0, 0 times 1 equals 0, 1 times 0 equals 0, and 1 times 1 equals to 1. That makes perfect sense. So we also refer to AND gates as a multiplication operator. So in this way, we can write any truth table we're given in a sum of products form. The products, together with inverters here, allow us to pull out individual rows that produce a 1 at the output, and then we simply OR them all together to get the desired truth table that we want. And so we're halfway there. Remember, our challenge was to write an exclusive OR gate using only NAND gates. It might look like we're a long way away, but at this point, given any truth table, we can write it using only AND, OR, and NOT gates. So if I can write an AND gate, an OR gate, and a NOT gate using only NAND gates, then I'm done. In other words, part 2, all we are going to do is we're simply going to replace every inverter with some NAND gates to get an inverter. We're going to replace every AND gate with a bunch of NAND gates to get an AND gate. And we're going to replace every OR gate with a bunch of NAND gates to get an OR gate. And then we're done. So in other words, the problem we have to solve right now, there are three problems. How do I write an inverter using only NAND gates? How do I write an AND gate using only NAND gates? And how do I build an OR gate using only NAND gates? And we'll look at this now. So let's start with an inverter whose truth table is this, and we have an unlimited supply of NAND gates whose truth tables are this. How can I get an inverter using only NAND gates? There isn't really a clever way of deriving this, or maybe there is, but it doesn't really matter. All we need to do is observe that if both inputs of my NAND gate are the same, then when I come to compute the truth table here, if 0 comes in, then 0, 0 on the input gives me a 1 at the output. Whereas if a 1 comes in, then 1, 1 at the input is going to give me a 0 coming out. And so we see that I can build an inverter using only a NAND gate simply by connecting the two inputs of the NAND gate together, and I get an inverter. So that solves the first problem. Every inverter I can replace by a NAND gate whose inputs are fused together. Next we consider the AND gate, and I'm only allowed to use NAND gates, but a NAND gate, even just by looking at it, is equal to an AND gate followed by an inverter. And if I want to get rid of that inverter, I just have to put it through another inverter. And so in other words, if I want an AND gate, I can get that by taking a NAND gate and putting the output through an inverter. And what did we just learn before? An inverter can be implemented using a NAND gate by fusing the two inputs together. And so therefore, to get an AND gate using NAND gates, I can do it like this. And you can check the truth table. You can verify that this block here really does give me an AND gate. Just check the truth table for it. Finally, we have an OR gate whose truth table is of course given by this. And our basic building block is a NAND gate whose truth table is this. And we have a look and we see when we compare these that both of them have got exactly 3 locations when the output is a 1. And so it's a bit like before. These gates look very similar. I just have to rearrange these two inputs. I need 0, 0 to act like 1, 1. If I can somehow swap those around, then I can implement an OR gate using a NAND gate. And we saw before that I can swap inputs around by using inverters at the input. And so that suggests, to me at least, that what we can do is that I can take the input, take both inputs in fact, and put them through inverters. Because then if I've got 0, 0 coming in here, after that goes through inverters, I'm going to have 1, 1 coming out here. And my NAND gate gives me a 0 when I've got 2 1s coming in. And so therefore, if I now put this through my NAND gate here, I expect that this circuit here implements an OR gate. And finally, let's check it. So there are 4 things I have to run through. Firstly, I ask what happens when the input is 0, 0. Well, if 0, 0 come in here, then I get 1, 1 here, and 1, 1 at the input to an AND gate gives me a 0. If I now have 0, 1 coming in, that means that going into my NAND gate, I'm going to have a 1, 0, and 1, 0 going into my NAND gate gives me a 1 at the output. So 0, 1 gives me a 1. If instead I've got a 1, 0 coming in, that means into my NAND gate I have a 0, 1, and 0, 1 going into my NAND gate gives me a 1 coming out. And finally, if I have got a 1, 1 going in, then after the inverter I've got 0, 0 going into my NAND gate, 0, 0 going in gives me a 1 coming out. So 1, 1 going in gives me a, what did we say, a 1 coming out. And indeed, this circuit here has got this truth table here, 0, 1, 1, 1, which is exactly the OR gate up here. If we want only NAND gates, then of course we just replace each inverter with an inverter made using a single NAND gate like we learnt before. So in other words, the answer is that our circuit looks like this. That is an OR gate. So let's put everything together to check we remember everything. If I want to implement an exclusive OR gate using only NAND gates, I first write down its truth table. Then I can derive the sum of product form by looking at this row, then this row. The first row with a 1 says that the input needs to be a 0, so I put an inverter here and a 1, no inverter. That goes to an AND gate. The second time I have a 1 here, the input is a 1 and a 0. So whenever I have a 1, it goes straight through to the AND gate. When I've got a 0, it needs to be inverted. And once I've done that for every single row with a 1 coming out, then I just put that through an OR gate. And I know that this circuit here implements this truth table here. So this will give me an exclusive OR gate. Now all that remains is to replace each of these gates here with NAND gates. So we know that inverters are made by just fusing together the two inputs of the NAND gate. So I've got, let me change colours. This part of the circuit here is given by this part of the circuit here. And similarly for the lower part, I've got this and this. These two blocks go into AND gates. To get an AND gate, I just put it through a NAND gate followed by an inverter. And so therefore this goes into a NAND gate followed by an inverter, but an inverter made using a NAND gate looks like that. Same as this, to put this into an AND gate, I put it into a NAND gate and then into an inverter. And now, and to emphasize here, so this part of the circuit here is this part of the circuit here. And now finally, all I need to do is put these two outputs here through an OR gate. But remember, an OR gate we get by inverting the inputs to a NAND gate. And to invert the inputs, I can use a NAND gate with its inputs fused. And so therefore, this OR gate here is given by these gates here. It's a good exercise, if you so wish, to write down the truth table for this circuit, where my inputs are A, B, and because I've called this input and this input A, it receives the same signal. So if you really wanted, you can add those extra lines in there. I'll do it in a different color. If you really wanted, you can have input A going to these two things and input B going to these two things. But if you write it using the same letter, people should understand what you mean. So this great big logic gate down here, it's got two inputs A and B and one output. And if you write down its truth table, it's going to have the same truth table as this exclusive OR gate. And we've been able to implement this exclusive OR gate using only NAND gates. Now, do you want to do this in practice? Not really, because you can just buy an exclusive OR gate and it's going to be better in many ways, which we're going to learn about later on when we consider the transient response of logic gates. But this is a good exercise to show you not only a little bit about Boolean algebra, we talked about addition and multiplication, etc., but about the sum of product form and how, given an arbitrary truth table, we can implement it using only NAND gates by going via the sum of product form. Now, technically, we only did this for 2 input gates, but the same process works for an arbitrary number of inputs. In the sum of products form, our AND gates and our OR gates need to accept more inputs, but then it's possible to implement an n-input AND gate using only 2-input NAND gates. And the same, we can implement an n-input OR gate using only NAND gates. And in fact, let's try to understand how we can do this now. Let's look at an AND gate first. Let's assume that I want to implement a 3-input AND gate, which we understand to mean the truth table is going to be 1, 2, 3, 4, 5, 6, 7, 8. So an n-input AND gate, its output is going to be 0 unless all the inputs are 1. How can I implement this using only 2-input AND gates? Well, one way is to just cascade them. And so hopefully you can see how this works. For the output here to be a 1, both the inputs here have to be a 1. And for this input to be a 1, the output of this AND gate has to be a 1, which means its inputs has to be a 1. So by going backwards like this, we see that the only way for the output to be a 1 is if all the inputs are a 1. So therefore, a 3-input AND gate can be implemented using only 2-input AND gates by cascading them like this. And the same idea works for a 4-input AND gate and for a 5-input AND gate and so forth. Now, again, this is not saying that this is the most efficient way of doing it. As an aside, I can also implement a 4-input AND gate in this fashion here. So there's not a unique solution, but at this point in the course, we're not worried about being optimal or anything like that. We're simply asking, can it be done? And the answer is yes. So if I have an n-input AND gate, I can write that using only 2-input AND gates. And each of these 2-input AND gates I can replace with 2 NAND gates, with 2-input NAND gates. And so therefore any n-input AND gate can be implemented using only 2-input NAND gates. The same thing applies to OR gates. If I have a 3-input OR gate, then that means that its truth table, which I'll do up here to save room, an OR gate, its output is only ever going to be 0 if all the inputs are 0, and otherwise it's going to be a 1. So therefore a 3-input OR gate has got this truth table here in blue. And I can implement it using 2-input OR gates by using the same cascading form. If I have got an OR gate here going into an OR gate here, then we can see quite easily that the only way that the output here is going to be a 0 is if both these inputs are 0, and the only way this can be a 0 is if both of these are 0. So therefore, the only way for this to be 0 is if this is 0, this is 0, and this is 0, which is exactly the truth table we want for a 3-input OR gate. And once again, each of these 2-input OR gates can be replaced by 3 NAND gates. I need 2 NAND gates at the front to be inverters and 1 more NAND gate, and I get my OR gate here. So what we've essentially shown is that any truth table can be implemented using only 2 input NAND gates. And we do that in an inefficient way, but it always works. We do that by writing the truth table in a sum of products form. That means using only AND, OR, and NOT gates, and then by replacing each of these 3 gates with NAND gates to implement them.